Hello, welcome to our channel again. So I'm Suraj and today we are going to prove a very important principle in the quantum mechanics, which is the Pauli exclusion principle. So I know that you all are familiar with that particular expression because this is a very good principle in the quantum mechanics that says that two fermions cannot acquire the same quantum state. So what is there? So thing is that we are going to prove that particular equation because every day we study about these equations, but I don't think so that we encountered the proof of that particular expression. So I'm going to prove the Pauli exclusion principle in that particular video. So let's start our today's video on the Pauli exclusion principle. So the proof of the Pauli exclusion principle is like that you have to deals with the identical particles. So I know that the topic that I am now saying, identical particle, is some sort of intermediate topic in the quantum mechanics which requires some basic knowledge. So if you want to know more about the quantum mechanics, you can watch my previous videos on the quantum mechanics where I discussed about the basics of the quantum mechanics. But remember, this particular proof is not for you because it's for a person who has a knowledge of some intermediate quantum mechanics, that what exactly the formalism is. So this is a video for those, not for those who has just started quantum mechanics and learn about the potentials, wave functions, expectations, value, normalization. So this video is not going for you. So just leave out this video. This is for the people who has some intermediate knowledge of the quantum mechanics. So let's start our video. So what we can do is that we are dealing with the identical particles, and we know that in identical particles, how we can define the wave functions of, let's say, two particles. Let's say I have two fermions, let's say electron. So this is the electron and this is the second electron, and their respective wave functions, let's say this is psi a1 and this is psi b, psi a and psi b. So how we can write it in a quantum mechanics expression? So let's see. So let's say we have defined a wave functions for two fermions. Let's say we have defined wave functions for the two fermions, which is the psi, let's say psi a and psi b. So as we can see here, there are let's say two fermions A and B here, psi A and psi B, their respective wave functions. So now in quantum mechanics, how we can write this in a particular good form? So collectively we can write their wave functions like this. Collectively, let's say they have a coordinate position R1 and let's say there is a coordinate position R2. So how we can write this? R2 and R1 are their respective coordinate positions. So psi R1 and R2. Okay, so here I'm not writing time because this is, I am taking about the time independent wave function, which is not same as the is general solutions of the wave functions that we study. So here we are dealing with the time independent. So this is very good things because time independent is very easy to work, as you can say that. So the thing is that we define the wave functions for both of this particular two particles, psi R1, psi R2. How we can do this? So plus minus. Why I am putting here plus minus? So let's see here. There is a very good thing to put here plus and minus, and it has some properties. Okay, let's say R1 and R2. How we can write this? We can write their wave functions collectively like A, where is A is a normalization constant, as a psi A R1, here psi A R1, psi B R2, here is the psi B R2, and minus plus psi B R1, psi B R1 and psi A R2. Okay, so this is the particular expression, so that how we can write their wave functions collectively, and this is the wave function how we can write. Here you can see that I've written plus minus and minus plus. What is the significance of this? So this particular expression can be written for fermions and bosons both. So what are bosons? We have no fermions, but what are bosons here? So you know that bosons are the particles which has integer spin. It means it has an integer spin like 0, 1, like this. But fermions, let's say, but the fermions has no integer spin. They have the half spin, which is 1 by half and minus 1 by half, exactly. So these are the fermions and bosons. So there is a distinction that for bosons, we use our wave function for plus sign. It means plus sign we use for our bosons and minus sign for our fermions. So this is the thing. So minus sign for our fermions and plus for our bosons. So as you can see here, I have written the wave functions. So the plus wave function, as you can see here, is for the bosons, and here the minus wave function is for the fermions. So let's see how we can derive this from our expression. So let's say we are saying that this particular a is equals to b. It means the wave function of psi a. It means I can write this in a very good form, that psi a is equals to the psi b. So this is a condition. It means both of their wave function are same. It means both of their states are same. So if we substitute this particular expression in our fermions, as you can see here, so if I substitute it here, you can see that this particular is converted into the a. This got converted into the a, and this expressions become identical. This and this will cut out, and what we are left is that there is no such wave functions for the particles, which is equal to the 0, because this becomes 0 and a to 0 is 0. It means for fermions it is not possible. It means their wave functions come out to be 0. What is the thing here? The wave functions come out to be 0. It means there is no such possible conditions that the two fermions can acquire the same quantum state. So this is the particular proof. What I have done? So you know that in identical particles we can write the wave functions, collective wave functions for the two particles like this. So plus is for the bosons and minus is for the fermions, we have written here. And if we substitute this particular thing psi a is equal to psi b in bosons, it doesn't come out to be 0. It means in bosons it is possible that two particles can acquire the same quantum state, but in fermions it is not possible that the two fermions can acquire the same quantum state. So this is a simple proof of mine on the Pauli exclusion principle. So this is a short proof on this. So thank you for watching my video.